Everyone, welcome back to the class of Calculus 3. We are working on triple integrals. Actually, this is the example we just finished. It is triple integral over a tetrahedron. And I believe I did all the, I don't necessarily did all the calculation. I finished all the important steps. And I skipped some calculation here, okay. It is 1/12. And the thing I want to mention here is, in general, I want you to know a triple integral over rectangular region. There are 6 ways to evaluate a triple integral, right? 6 ways. And also for tetrahedron, there are 6 ways. There are 6 ways. And also, to save time, I'm not going further to show more ways. As I'm saying, it is a good exercise. You may want to give a try if you are watching the video. Maybe take a pause. Try to see if you can write out the other 5 ways. The other 5 ways to evaluate this triple integral. Okay, and it is complicated. And sometimes, if you are lucky enough, when you have triple integral, you can start in any order, any way you want. But anyway, mostly, as you may imagine or expect, the order doesn't matter. So the next example I'm doing here, it is still from the textbook. I'm talking about example 5.41, I'm sorry. We are evaluating a triple integral of this thing. And the solid, it is bounded by the paraboloid. And up to the plane y = 4. It's from this lower portion, everything inside the paraboloid surface goes up to y = 4, up to y = 4. And like in this case, I would say mostly, I don't know about you, to evaluate a triple integral, eventually we'll have to deal with double integral. So I would say maybe the most convenient way, or maybe the way the first to come to my mind, maybe we want to consider try to evaluate the integral in terms of z first, and then hopefully z will vanish. After z vanishes, we can consider the integral into the xy plane, double integral into the xy plane. Usually, I would say for now, maybe that is the situation, that is our comfort zone, how we evaluate the double integral into the xy plane. So besides, if you look at the projection of this solid into the xy plane, I hope you see clearly it is bounded by the parabola, right? Parabola, and the line y = 4. I suppose we can handle that. We can consider this as a type 1 region. And also, if we just want to go this way, which really means we are going to evaluate this integral in terms of z first. Z first, okay. Keep in mind that z is not going in the y direction, going along the vertical direction, going along the z-axis. So it is from the same surface, if you think very carefully. Along the z direction, the surface on the top really the same as the surface at the bottom. Certainly, because of symmetry, everything on the top for the z coordinate is positive. Everything below the xy plane, z coordinate is negative. So this is the arrangement. If we want to get to the comfort zone, starting from z and then get into the xy plane. Z, I hope it makes sense. Okay. Z, it is observed from this paraboloid surface. And the paraboloid surface, it is this fashion. So we solve for z. Z squared, it is x squared minus y. Did I get x squared minus y? Z squared is y minus x squared. It should be correct. Then to the top of the surface, it is the positive root, right? So I have a square root of y minus x squared. To the lower side, it is the opposite of the top. So that's minus the negative root. And then indeed, and also we did figure out how to identify the region in the xy plane. Okay, it's a type 1. So x is changing from -2 to +2, 2 constants, no doubt. y depends on x. The lower portion, it is a parabola. The upper part, it is just this orange or brown colored line here. So we do have the description of the solid into x, y, z perfectly. And also, as I'm thinking, I am going with, and also really according to this description, basically we are going to go with z first. With z first, okay. With z first. And this is the correct arrangement. If we follow the description of the solid in this fashion. But there are few other things you may want to take a look again. First of all, if we evaluate in terms of z first, we are having z squared inside the square root notation, right? The x squared or y squared, or indeed we are just having x squared here, somewhat they don't matter at this moment. The only thing matters it is z squared. But anyway, it is inside the radical notation. And you may want to give a try to see if you really can have the antiderivative z. My guess, it won't be very easy to get antiderivative z squared inside the radical notation. Besides, if you are getting the antiderivative successfully, you may want to know you are going to plug in the square root into that z, and probably it still will have to involve with another square root outside. And also there are other things, there are powers involved. So I say for now, I really want to say it's very hard for me to figure out how the antiderivative in terms of z would look like. Besides, I'm a little worried even after getting, if I get antiderivative, how do I handle the other pair of square roots again? Okay, so as the textbook said, the exploration, it is difficult or very difficult. I say maybe impossible. Well, it is, I don't want to say impossible. It is very difficult. Okay, so what we consider here is that we may want to start to consider the integration into another fashion. And maybe not instead of z first, because you look at the actual drawing, three-dimensional drawing here. Okay, if you look along the y direction, the circle in the front, right, which covers everything, and then the lower portion of the surface is the parabola, and indeed the projection of this paraboloid, it is also of the same circle. So if we look at the integral in terms of y first, those two squared, perfect squared, would turn to be the lower bound. 4, it is the upper bound. And besides, one thing I just realized here is that after evaluating y, we would have a circle in the xz plane. Whenever we have circle, possibly we could use the polar coordinates. So this is the other arrangement. Okay. We are considering y first. We are considering y first. We are considering y first. X squared plus z, I think, did I get this part correctly? X squared plus z squared equals 4. And then what I meant to say here is in terms of c, actually this bound is not correct. I think it should be x squared plus z squared, right? Because y is given as x squared plus z squared. So the lower bound, indeed, it is x, see? The lower bound, it is x squared plus z squared. And this portion really goes to 4. Yeah. This portion just goes to 4. And then also I needed to update the bound for dy dx for y first. Control C. And this part should be plus part. Yeah, it should be this fashion. It should be this fashion. And then in terms of order z first, dc, dy, dx. Okay. And then after evaluating in terms of z, we would have dy dx left. And am I correct? Oh, this we are doing I'm sorry, it should be dy then dc dx, and then this should be dy dc dx, and then this should be dc dx. Okay, and now I think this part should be, I should have this entire writing corrected. And now you want to think this very carefully. To this moment, somewhat we kind of get to the same situation. We still will have to handle z squared inside the radical notation. Okay, in general, it is not that easy. It is very hard. But we do understand the region we work on in the xz plane. It is circle. Whenever we have a circle, usually it's a lot easier if we consider polar coordinates, right? So indeed, in the xz plane, well, using the polar coordinates, this is y really should be z in the xz plane. Okay, and also don't forget that this dz dx part, it is really for the double integral, right? Double integral, so it is dA. And when we use the polar coordinates, the dA, it is replaced with r dr d theta. Okay, and also don't forget x squared plus z squared, which is really r squared. The square root of r squared is r, and this is 4 minus r squared. 4 minus r squared. Square root of r squared r dr d theta. So indeed, this part, I'm going to say you want to evaluate this square root of r squared is just r times r squared. So it's 4 minus r squared minus r to the 4. And in the end, I believe the answer it is 128 pi over 15. So this is the way to evaluate a triple integral. A triple integral, there are 6 ways to evaluate a triple integral, like for the tetrahedron. And also, I hope it's a lot easier when we deal with triple integral when we have a rectangular solid. So I'm going to roll back to the solid part, rectangular box part. Okay. And sometimes the order does not matter, but I would say in general, the order does matter. Like the integral we discussed over here. If we insist with z first, and it is possible to set up the integral to get started, but once started, it would be very hard to evaluate the antiderivative. So instead, what I consider here is I look down the solid along the y-axis from the front to the back. I'm seeing circle as the top surface, and the projection of the lower surface, that's the same circle, which really allows me to evaluate the integral in terms of y first. So this is what I did. Okay, then after doing the inner part of the evaluation, dy, dz, dx, what I get here is, well, it turns out to be this. It turns out to be this. And still, if you are thinking about z and x only, it's still very hard. Okay, but we do understand that in the x, y, z plane, that has to be a circle. That is a circle of radius 2. That is a circle of radius 2. Okay, that is circle of radius 2. So using polar coordinates to the xz plane, I figured out the triple integral. It is reduced into a double integral. This double integral, it is evaluated using polar coordinates. In the end, we figured out this number here. So this is the beginning part of triple integral in section 5.4. Thank you for watching.